Laurel and Hardy were brought in for a chest X-ray. All right, I hope you've seen a few episodes of Laurel and Hardy. It is quite an old television series, right? In the olden days, it was to air, but it is a very funny one. So Laurel is this thin-built guy, and Hardy is the one who is sort of a bully and has a very healthy build. So Laurel and Hardy were brought in for a chest radiograph. Laurel's X-ray was done using a 80 kV and 6 MAS. What is kV? Kilovolt peak, right? What is MAS? Milliampere seconds. These are important exposure factors in X-ray. We are going to study them in detail and how they affect the X-ray beam. Considering Hardy's body habitus, which of the following should be the most appropriate change which should be done now after doing Laurel's X-ray, right, such that a good X-ray radiograph can be obtained? So this is sort of an application based question. The technician, X-ray technician, has to change the KVP and the MAS every time he does a chest X-ray depending upon the patient's body habitus. How should he change it? How it will affect the X-ray beam quality is something that this question is focusing on. So we'll discuss this when we discuss KVP and MAS in detail. Yes. Now friends, before we jump into the structure of the X-ray tube and see how X-rays are actually going to be produced, we must have to build a foundation regarding the structure of the atom, because this is important. This is going to help us understand X-ray production better. So I hope you've all heard the name of a scientist by the name of Niels Bohr. Yes, Niels Bohr told us what is the structure of the atom. What did he tell us? He told us that the atom basically consists of a central nucleus and electrons orbiting around the nucleus in certain shells. He called these shells as K, L, M, N, so on and so forth. Yes. He also told us that each of these shells could contain a certain fixed number of electrons. K shell could contain 2 electrons, L shell could contain 8 electrons, M shell 18 electrons, so on and so forth. He told us that if all the shells are completely filled by the required number of electrons, then the atom, such an atom, would become a stable atom. Isn't it? Now, at this point, I want you to just consider that this atom that I am showing you here is an atom of tungsten. Why tungsten? I'll just come to that in a minute. Now, look at this tungsten atom. In this tungsten atom, I want you to focus on this inner shell electron, that is K shell electrons. Look at this particular K shell electron. Tell me whether this K shell electron, is it a free electron? Is it free to go about wherever it likes? Or is it a bound electron? I'm sure you would get that it is a bound electron in the sense that this negatively charged electron that lies in the K shell, it is bound inside this atom by the positively charged nucleus, which is very close to it, isn't it? And therefore, this electron has to stay in this K shell. It cannot move out of the K shell. Therefore, because it is bound in the K shell by this positive charge of the nucleus, suppose I decide to do an experiment. And what is that? In that experiment, I want to catch hold of this particular K shell electron and I want to pull it out of the atom. I want to make it a free electron in outer space away from the influence of the nucleus. Now, what is a free electron? Remember, just for the sake of definition, I am telling you, a free electron is an electron whose total energy level is equal to 0. That is the definition of a free electron. Free electron total energy level is equal to 0. Now, let us start at the original premise that we started. Tungsten atom. Inside the tungsten atom, the inner shell electrons, and now I am going to do that experiment. See, when this experiment was actually done by scientists, what did they do? They caught hold of this particular electron, they removed it out of the tungsten atom, made it a free electron in outer space, right? They realized that in order to remove this K shell electron of tungsten atom, right, they had to spend an energy which was equal to around 70 electron volts. How much energy was required to remove it? It was 70 electron volts. Now see, such a simple experiment I have conducted. I have removed this K shell electron, made it a free electron. In the process, I have spent 70 electron volts, right? So now I am just going to write it down mathematically. Just see, I am saying that if X was the original energy level of this K shell electron, in this experiment I have given this electron an energy of 70, that is what I have spent. So what is the result? The result is that the electron has become a free electron. And what is the energy level of a free electron? Definition we have studied, that is 0. So what is this equation? X plus 70 is equal to 0. Do you all agree with this equation? Yes. Now, therefore, using this simple equation, tell me what is the value of X or the original energy level of this particular electron? X is going to be equal to minus 70. What is this minus 70 or X? I said it is the original energy level of this K shell electron. Here I want to introduce you to a very important concept. That is the first concept about the structure of the atom. What is that? The concept says that each shell in an atom has its own fixed energy level associated with it. Right? All the electrons in that particular shell must lie at that specific energy level only. So we just studied what is the energy level of K shell of tungsten atom. It is minus 70. So all the electrons in the K shell, they will lie at what energy level? Minus 70. Now just tell me, just imagine if the amount of energy required to remove this K shell electron was 70 electron volts. What will be the amount of energy required to remove this L shell electron? Will it be more or less? It will be less, right? Why? Because this L shell electron is located slightly away from the nucleus. It is slightly loosely bound. So when an experiment was conducted, scientists found that the energy required to remove this L shell electron is how much? It is 12 electron volts. And therefore, what will become the energy level of L shell? Same equation if we use, it will be minus 12. Similarly, the energy required to remove the M shell electron was just found to be 2 electron volts. So, what is the energy level of M shell? It is minus 2. I hope you got the first concept. Each and every shell in an atom has its own fixed energy level associated with it. All the electrons in that shell lie at that specific energy level. What are the energy levels in a tungsten atom? It is minus 70, minus 12, minus 2 for KLM shells respectively, so on and so forth. This is the first concept. Energy level is specific for a particular shell. Each shell has an energy level. Now, the second concept that we are going to study is just an application or extension of the first concept. Again, we come back to this tungsten atom. Remember that experiment we conducted? I have pulled out a K shell electron. So, what is the result? The result is that initially, this particular K shell had 2 electrons. Now I have removed 1 electron. So what happens now? There is an empty space called as an electron void which is created in the innermost shell. Just imagine, I have removed a single unpaired electron from the innermost shell of the atom. Naturally, the atom has become unstable. The atom wants to become stable. Natural tendency of matter is to always go towards a state of stability, isn't it? So this atom wants to become stable, right? How will it become stable? Tell me. Can you imagine what will happen? What happens in such a scenario is that an electron in the next shell, that is the L shell, is going to jump into the K shell. Then an electron from M shell will jump into L shell. N shell will jump into M shell. So on and so forth until all the shells are again filled. A free electron comes and lies in the outermost shell. Atom becomes a stable atom. But when this jumping of electron happens, see here what is going to happen. This electron is located in the L shell. Its energy level is minus 12. I said it is going to jump into K shell. What is the energy level of K shell? Minus 70. So tell me, when this electron jumps from the L shell to K shell, minus 12 to minus 70, what it has to do? Whether it has to gain energy or lose energy? Yes, gain or lose? Yes, friends, I hope you realize we are on the negative side of 0. So minus 70 is significantly less than minus 12. So what this jumping electron will have to do? The jumping electron will have to lose some amount of its energy. What is the amount of energy lost? It is the difference between them. So minus 12 and minus 70, difference is what? Difference is 58 electron volts, which will be lost. It will be given out. Now the energy level of electron is minus 70. Now can it lie in the K shell? Yes, it can. So what is the second concept? The second concept is that whenever an outer shell electron jumps to the inner shell, what it has to do? It always has to lose some amount of its energy. Did you get these two concepts? Firstly, we studied every shell in an atom has its own fixed energy level associated with it. All the electrons in that shell must lie at that specific energy level. Second, we studied whenever an outer shell electron jumps to inner shell, it always has to lose some amount of its energy. Why is it necessary to study these concepts? It is very important because now you'll realize in the next few minutes when we study production of X-rays, this is going to help us in our understanding there. So let us now go to the X-ray tube. When you walk into a radiology department, you go into a X-ray unit, the X-ray room, you will see an X-ray machine attached, or to a vertical arm of the X-ray machine, you will find an X-ray tube. It looks white like this. Why? Because what you are actually looking at is the outer surface of the X-ray tube. This is called as the tube housing. What is the tube housing? Tube housing is basically a lead lined material, right? Why lead lined? Because X-rays are going to be produced inside the tube. So this lead lined material prevents the leakage of radiation, and therefore it protects the patients and the department staff from this leakage radiation. And that is the function of this particular tube housing. Now let us open up. We want to study a detailed structure. So we open up the X-ray tube. When we open up the X-ray tube, what do you find? The tube housing is open. What do you find inside? Inside the tube housing is an oil bath which is there. Why is this oil used? This oil bath which is placed inside the tube housing, it surrounds the tube envelope. So outermost is tube housing, which is filled with oil. In that oil or oil bath is kept a tube envelope. Remember, so this oil plays a very important role because it surrounds the tube envelope and it helps dissipate the heat which is produced from the tube components. So the oil has a heat dissipation a role to play. Inside that oil bath is placed, we discussed, a tube envelope. This tube envelope is actually made up of glass in the older X-ray tubes. In the newer X-ray tubes, it is made up of ceramic. Again, it has a very high heat loading capacity. Heat tolerance is very high. Now let us open up the X-ray envelope or tube envelope also, and you'll find that in the tube housing and tube envelope, there are certain ports for attachment of electrodes. One is called as the cathode port, one is called as the anode port. That is where the cathode and anode connections are going to be made. There is a window which is placed in the tube housing as well as envelope, and this window is called as the exit port. Why? Because X-rays are produced, X-rays have to come out from somewhere. So this is the exit port from where the X-ray beam is going to come out. Now this exit port restricts the primary X-ray beam exiting from this port. Rest everything is lead lined, the tube housing. So rest X-ray beams cannot come out from anywhere. They come out only from the exit port. At the exit port, you will find that there are sometimes filters which are attached. What do these filters do? They block low energy X-ray so that X-ray beam of only the diagnostic intensity, right, or strength is going to come out. Then there are collimators are placed. See, for example, if you're supposed to do a wrist X-ray, you will require a very narrow beam, right? So the collimators, lead collimators will give out only a narrow beam. But when you are supposed to do a chest X-ray or an abdomen X-ray, you need a very wide beam. So the collimators will open up and they will create a wide beam, right? So that is what is the role of collimators. So this is how the external structure is. Now let us go inside the tube. Now inside the tube you will find is vacuum. So inside the tube envelope there is vacuum, and in this vacuum there are two important electrodes which are placed. One electrode is called as cathode, the other one is called as anode. We are going to study them in detail. But before we go there, remember, why is cathode called as a cathode? Because it is given a very high negative charge. Remember, so it is called cathode. The anode is given a very high positive charge. So it is called as anode. So just see, cathode is very negative, anode is very positive. And so if you look at the potential difference between the cathode and anode, I hope you realize that this is a very, very high potential difference, isn't it? This high potential difference between the cathode and anode plays a very important role in production of X-rays. How? We are going to see that. Now, let us focus on the cathode first. Now, when we focus on the cathode, right, I want you to know that this cathode is nothing but a cathode filament or a wire. This wire is made up of tungsten, right, and it is just a helical wire, right? Do you remember when we studied tungsten? I told you tungsten is a very important component of X-ray tube, right? Why? Because the cathode filament is made up of tungsten. So it is a thin helical wire around 10 to 20 millimeters in length and around 2 to 5 millimeters wide. A tungsten wire is there. Now let us see how it is going to work. Now a small circuit is attached across this tungsten filament or cathode filament, and when you switch on the X-ray tube, what happens? A small electric current is being passed through this particular cathode filament. Can you see the electric current there? So electric current is passing through this filament. So what is going to happen? Once an electric current is passed through it, remember tungsten is a very heavy metal, so it has a very high resistance to the conduction of electricity. So what is going to happen? Because of this high resistance to the conduction of electricity, this tungsten filament is going to get heated, right? What happens to those immersion water heaters that we use? What is there inside it? There is a high resistance coil. When you switch it on, you put it in water, the water is going to get heated. Heat is produced when you pass electric current through a high resistance wire. Same thing is happening here. So the tungsten filament is going to get heated. Now when it gets heated to very, very, very high temperatures, right, what is going to happen is that there is a very beautiful phenomenon that occurs at the level of the cathode filament. This phenomenon is called as thermionic emission. Don't worry, it is a big word, but I'm going to simplify it for you. Let us split it up into three parts. Look here, thermionic emission. Now let us see it one by one. Whenever there is thermal energy or heat which is produced, what will happen? There will be ionization. Whenever there is ionization, what will happen? There will be emission of electrons. So what is the result of thermionic emission? Thermionic emission will result in emission of electrons. Can you see there? Electrons are being emitted out from the cathode filament. These electrons, when they are emitted, remember inside the tube there is vacuum. So these electrons are going to accumulate around the cathode filament as a cloud of electrons which is going to form around it. So just see now, look at the X-ray tube. There is a cloud of electrons which is formed around the cathode filament. Now what is going to happen? Do you realize that inside the tube there is vacuum, and I told you there is a very high potential difference which is applied between the cathode and the anode. The cathode is very negative, anode is very positive, and we know that opposite charges will always attract. So what will happen to these negatively charged electrons? These negatively charged electrons which are accumulated as a cloud of electrons around the cathode filament will naturally be attracted towards the anode, right? But do you remember I told you that the potential difference between the cathode and the anode is very large? So what will happen? So these electrons are not just attracted or not just pulled towards the anode, but rather they are accelerated towards the anode. Look at the animation there. Can you see that this cloud of electrons is very rapidly being pulled towards, or rather accelerated towards the anode? So what is going to happen? When they are accelerated, they are moving at very high velocities, very high kinetic energies, and with this high velocity and this high kinetic energy, they are simply going to go and hit the anode. And when they hit the anode, something magical is going to occur. What will happen? Let us shift our focus now to anode. Look at the anode. What is going to happen? There is a high velocity stream of electrons coming and hitting the anode, and therefore it is called as the anode target because it is getting hit. A lot of heat is going to be produced at the anode, and therefore the anode must be of very high atomic number. It must have a very high heat tolerating capacity, isn't it? What is the anode made up of in an X-ray tube? An anode most commonly used in an X-ray tube today is a alloy of tungsten comprising 90% of it and rhenium comprising 10% of it. This is the most commonly used anode material. In certain X-ray tubes, molybdenum is also used, especially in mammography X-ray tubes. Molybdenum is used as the anode material. Now in olden X-ray tubes, the anode was stationary anode. So it was just like a metal sheet there. It was hit by a high velocity stream of electrons. A lot of heat was produced. When metal is heated, it expands. When it cools down, it retracts. When it is heated, it is expanded, right? When it cools, it retracts. So this expansion and retraction gives rise to a very irregular shape of the anode. So it had to be replaced, right? Did not have a long life. X-ray tube malfunctioned, right? But nowadays what they do is, instead of using a simple disc, it is a rotating anode. Can you see the animation there? The anode is rotating. Because it is rotating, do you realize that every time the electrons are hitting a different part of the disc? Therefore, it is not easily deformed. It has a very, very high heat tolerating capacity and a much longer life. Now we have seen until this point how an X-ray tube actually works. Right, let us quickly go back. Let us rewind and start from step 1. Look at this X-ray tube. It has a tube housing. We open it. Inside there is an oil bath, inside which there is a tube envelope. There is a cathode port, anode port. There is an exit window with filters and collimators. Inside the tube envelope there is vacuum. There is a cathode filament made up of tungsten. There is an anode target which is also made up of tungsten, rhenium alloy or molybdenum. When you start the X-ray tube, what happens? When you start the X-ray tube, an electric current is passed through the cathode filament. Can you see that? Yes, now this cathode filament made up of tungsten is going to get heated. When it is heated, there is thermionic emission. There will be emission of electrons which accumulate as a cloud of electrons around the cathode filament, right? These negatively charged electrons are now going to be pulled towards the positive end, that is the anode. Rather not just pulled, they are accelerated, travel at very high velocities, and then when they go and hit the anode, this is where magic happens. Well, what happens inside the anode is some beautiful mechanisms occur, and the result of which, my friends, is the production of X-rays. Can you see the X-ray beam coming out of the X-ray tube there from the exit window? So X-rays are produced when? This is a question frequently asked. As you can see in the animation here, X-rays are produced when the high velocity stream of electrons hits what? It hits the anode, right? A rotating anode is very commonly used these days. That is all you need to know about the production of X-rays, the structure of the X-ray tube, and how it actually works. Now I'm going to take it one notch higher. Let us go inside this anode and see what are the actual mechanisms of production of X-rays. This has also been asked as an MCQ once. It could be a potential MCQ in the coming days. Now there are two ways in which X-rays can be produced. One is what is called as the continuous spectrum. The other is called as characteristic spectrum. What is this continuous and characteristic spectrum? Let us start one by one. Let us discuss first what is continuous spectrum. Continuous spectrum is also called as Bremsstrahlung, German term, right? It is also called as white radiation or braking radiation. Why is it called braking radiation? We will see that in this animation. Remember, this continuous spectrum is the most common mechanism of production of X-rays. It contributes to how much? Almost 70 to 80% of the production of X-rays. So whatever X-rays we use in our clinical practice, they are produced predominantly from this continuous spectrum. Now let us see how it works. Now consider here that this is a nucleus, this is an atom rather, which is located in the region of the target anode. Where is this atom located? It is located within the anode. We all know that an anode is going to be hit by a high velocity stream of electrons. So here is an electron which has come, which is traveling at very high velocity. I have paused it for you, right? Now just imagine that when this electron moves at very high velocity, I am going to run it in slow motion for you. Actually the electron is moving very fast. When it, when I run it in slow motion, see, this electron is come into the anode, and here it is coming and lying at a point which is very close to the nucleus of this particular atom. Right? Pause again, right? So see, this electron has come and lies very close to the nucleus. Now the electron has a negative charge. This nucleus has a positive charge. So they are bound to interact with each other. Now when they interact with each other, because of the opposite charges, they are going to attract towards each other. The nucleus cannot move, but the electron can move. So this electron, instead of traveling in a straight line like this, it is going to get deviated or deflected or decelerated from its original path, like this. Just see this again. An electron comes and lies at a point very close to the nucleus. Because of the opposite charges, they are going to interact, and it is going to get deflected or decelerated from its original path, deviated. So when it gets decelerated, do you realize that this electron is going to lose some amount of its kinetic energy? I said it is going to travel with very high velocity, very high kinetic energy, but when it is deflected, it is going to lose some amount of its kinetic energy. And this kinetic energy, which is lost by this electron, is going to come out of the X-ray tube as X-rays. That is where our X-ray production is going to occur. Remember, this is very simple underlying mechanism, and that is actually based upon something that we have studied in our school days. That is the law of thermodynamics. It states that energy can neither be created nor can it be destroyed, but it can be, yes, you remember, converted from one form to the other. So what is going to happen here? The kinetic energy of the electron which is lost is getting converted into energy content of X-rays. This is how X-rays are produced. This is what is called continuous spectrum. But why continuous spectrum? Right? Look at the mechanism now. Just tell me, when the electron comes and lies, at a point close to the nucleus, is the distance between this electron and the nucleus fixed or variable? It is variable. It can be any distance. So if the distance is variable, the interaction is going to be variable. If interaction is variable, the angle of deviation will be variable. If angle of deviation or deceleration is variable, amount of kinetic energy lost will be variable, isn't it? And therefore the energy content of X-ray beam will be variable. That is where the energy comes from. Therefore, if I measure the entire X-ray beam which is coming out, various rays which are coming out, and I plot it graphically, the intensity or strength of the beam versus the wavelength of the beam, I would get that I will get a continuous variable spectrum of energies, not a fixed value. Each time the energy lost is different, each time the energy content of the beam is different. Because I get a continuous spectrum like this mechanism is called continuous spectrum. Now let us look at what is called as the characteristic spectrum. Remember, characteristic spectrum contributes to only around 20 to 30% of X-ray production. It is the one, however, that has a specific application. It is used in a diagnostic technique which is called as mammography. So how does it work? See here. Again, we consider an atom which is located inside the anode. Where it is located? Anode, inside the anode, that is where X-ray production occurs. A high velocity electron is going to come, and now it is going to directly strike an inner shell electron. A head-on collision occurs. So when a head-on collision occurs with an inner shell electron, the traveling electron is traveling at a very high velocity, very high kinetic energy. So it is going to throw out the inner shell electron. The inner shell electron is thrown out, right? The traveling electron is also given all its energy to it. Now when an inner shell electron is thrown out, see, the atom has become unstable because there is one electron less in the innermost shell. The atom wants to become stable. Do you remember we have studied the concept? What happens whenever there is an electron void or an empty space in an inner shell electron? How does the atom become stable? An outer shell electron is going to jump to the inner shell. But we also studied what has to happen whenever an outer shell electron jumps to the inner shell. It always has to lose some amount of its energy, isn't it? So when a L shell electron jumps to the K shell here, what is going to happen? Some amount of energy will be lost, and this amount of energy which is lost or given out comes out of the X-ray tube as X-rays. That is how X-rays are produced. This is called characteristic spectrum. But why is it called characteristic spectrum? See here, whenever we look at an atom, the energy levels of each shells are fixed. So the differences between the energy levels are also fixed. And therefore, when an electron jumps from one shell to the other, a specific or characteristic value of energy is going to be emitted out. So if I analyze this X-ray beam, I will not get a continuous curve like this. Rather, I will get certain characteristic peaks on it depending upon what shell electron is jumping to what shell. Therefore, it is not called continuous spectrum. It is called characteristic spectrum. This is how X-rays are produced by the characteristic spectrum. Now let us revise and compare continuous spectrum and characteristic spectrum mechanisms of production of X-rays. Now continuous spectrum, remember, is the most common mechanism we studied for production of X-rays. It contributes to how much? Almost 70 to 80% of production of X-rays. Characteristic spectrum is less common. It contributes to only around 20 to 30%. Continuous spectrum, the X-ray beam which is going to come out is going to consist of beams of varying energies or varying intensities, and therefore when we plot it graphically we get a continuous spectrum. That is the reason for the name. Characteristic spectrum consists of beams of fixed energies or characteristic energies, and therefore we get characteristic peaks superimposed on the spectrum, and that is the reason why the name is so. Now continuous spectrum is used predominantly everywhere in the diagnostic radiology department, whereas characteristic spectrum is the one which is used predominantly in mammography. This was a question which was asked. In mammography, it is the characteristic spectrum type of radiation which is coming out from a molybdenum target anode. Molybdenum, the anode is made up of molybdenum, and characteristic spectrum radiation coming out from a molybdenum anode is what is used predominantly in mammography. Now friends, let us have some fun with this X-ray beam which is coming out from the X-ray tube. Now tell me, how is this X-ray beam used clinically? When you go to an X-ray room and you actually see how an X-ray is being done, you would realize that the patient is positioned in such a way that an X-ray film or an X-ray cassette lies on one side of the patient and the X-ray tube is on one side. So the X-ray tube is going to produce an X-ray beam. This X-ray beam is going to pass through the patient's body. As it passes through the patient's body, it is going to create a radiographic image of the patient's body, and then it is going to come out of the patient's body on the other side. It is going to reach the X-ray film, and that is where the image is going to be captured. Now there's something interesting which occurs inside the patient's body, and that is what is called as interactions of X-rays with matter. So let me be absolutely clear. I'm going to repeat it again. Tell me, what is the meaning of interactions of X-rays with matter and where do they occur? This is the way in which, these are the various ways in which the X-ray beam is going to interact with the patient's body tissues. So whatever happens inside the patient's body, when the X-ray beam enters into the patient's body, this is called as interaction of X-rays with matter. Yes. Now, so when an X-ray beam enters into the body, there are actually 5 basic interactions which can occur. These are Compton effect, photoelectric effect, coherent scattering, photo disintegration, and pair production. So these are 5 important interactions of X-rays with matter, out of which the first 2, that is Compton effect and photoelectric effect, are the most common ones to occur. So we are going to discuss Compton and photoelectric effect in utmost detail. Then we'll go to the other 3 which are not commonly seen. Let us start. So what is this Compton effect? Remember, just look at this animation. Now this is an atom located where? This is an atom located within the patient's body. So what is going to happen? An X-ray beam is coming into the patient's body. Now just see what is going to happen. This X-ray beam is coming and it is going to hit an outer shell electron of this particular atom. So where is it hitting? It is this X-ray photon or X-ray beam is coming and hitting an outer shell electron. Now see, the outer shell electron is very far away, from the nucleus, so it is very loosely bound. So to remove this outer shell electron from this particular atom, a very small amount of energy will be required. Just imagine that if the X-ray beam comes in with an energy of say 100 units, out of this 100 units, only 5 units is required to remove this outer shell electron when this collision occurs. That 5 units is given to that electron, the electron is thrown out of the atom. This electron is then called as the Compton electron. But what happens to the X-ray beam or X-ray photon? See, the X-ray beam traveled in a straight line with an energy of 100. It has lost 5, but 95 is still remaining. And then because of this physical collision which has occurred, what happens to the X-ray beam? Do you see this animation? Do you realize that the X-ray beam has now deviated from its original path? So quickly, what is happening in Compton effect? See, look at the animation. The X-ray beam is coming and hitting an outer shell electron. The outer shell electron is being thrown out, but the X-ray beam is getting deviated. So what is Compton effect? Compton effect is an interaction of an X-ray photon, as you can see here, with an outer shell electron, isn't it? With an outer shell electron. This is the most common interaction of X-rays with matter. Remember, this interaction is also known as the mid-energy phenomenon because it occurs more predominantly if the X-ray beam comprises of middle energy values, neither too high, neither too low, right? This is beyond the scope of our discussion at this point. I just want you to remember it is mid-energy phenomenon. Now, what is the result of Compton effect? See here, just imagine now, right, here is a patient and I am trying to do a cervical spine radiograph. So an X-ray beam is entering into the cervical area or the neck area of the patient's body, but because Compton effect has happened, and in Compton effect what happens to the X-ray beam? It gets deviated. So the X-ray beam will now get deviated, right, and it will reach the X-ray film at this point. Do you realize that an X-ray beam that has entered into the neck region has reached the X-ray film in a region corresponding to the head of the patient's body? It is carrying information from the neck. It has reached the area corresponding to the head on the film. So if I develop this film, I will get a much distorted image. This deviation of X-ray beam, right, that happens in Compton effect is one of the most important outcome of Compton effect, and this is what is called as scatter radiation. What is this scatter radiation? It is deviation of X-ray beam, and we just discussed what is the result of scatter radiation, right? It is going to give rise to image distortion. Image blurring is going to occur. Therefore, tell me, if the outcome of Compton effect is scatter radiation which causes image blurring or image distortion, do you want more Compton effect or do you want less Compton effect? We want less Compton effect because we want less scatter radiation, which will result in less distortion, isn't it? And therefore, we as radiologists, we clinically always try to minimize the Compton effect as far as possible. How can we minimize it? We can minimize by using high energy X-rays, because Compton effect, I said, is a mid energy phenomenon. So if we use a high energy X-ray beam, Compton effect can be reasonably minimized. This is what is about Compton effect, that is interaction of X-ray photon with an outer shell electron. That is what you can see in this animation. Exactly opposite, more or less opposite, because it was outer here, so it is going to be inner next, and that is what is called as photoelectric effect. What is photoelectric effect? Let us look at the animation first. So here is an atom in the patient's body. An X-ray photon is going to come and it is going to hit now an inner shell electron. Do you realize that an inner shell electron is very tightly bound by the nucleus? So if the X-ray photon has come with 100 units of energy, the entire 100 units is required to remove this electron when the collision occurred. So what happens? The X-ray beam gives all its energy to this electron, right? And the X-ray beam completely disappears. This electron has received this energy, this electron is thrown out of this particular atom. The atom becomes unstable because there is an electron void in the innermost shell, but an outer shell electron jumps to the inner shell, releases some energy. A further outer shell electron jumps to the previous shell. So that is how all shells will become filled. Eventually the atom in the body will become a stable atom. This is what is called as photoelectric effect. So what is photoelectric effect? Let us rewind and revise. Photoelectric effect is an interaction of X-ray photon with an inner shell electron, as you can see here in the animation. It is a less common interaction as compared to Compton effect. Compton effect is the most common one to occur clinically. Photoelectric effect is less common to occur. Compton effect was called as mid energy phenomenon. Photoelectric effect is called as low energy phenomenon. That is, it occurs more predominantly if we use a low energy X-ray beam. What is the outcome? Do you remember in Compton effect I showed you there is a deviation of X-ray beam, so scatter radiation, which causes image blurring. Here what is happening to the X-ray beam? When the X-ray beam hits the electron, the X-ray beam gives up all its energy. The X-ray beam has disappeared, right? Will there be any scattering therefore? There will be no scattering in photoelectric effect, and therefore rather remember, because of scatter radiation, Compton effect causes image distortion, image blurring. Photoelectric effect improves the overall image quality. Because it improves the overall image quality, we want to maximize the photoelectric effect. How can we maximize photoelectric effect? Look, it is called as low energy phenomenon. So if we use an X-ray beam of relatively low energy levels, or we use a target of relatively high atomic number, we will be able to maximize the photoelectric effect. Now very often I am asked a question, sir, how is it that a low energy X-ray beam is going to hit an inner shell electron and remove it because it is very tightly bound? See, these are all relative terms. When I mean a low energy X-ray, this low energy and content of this X-ray beam is actually perfectly suited to remove the inner shell electron of atoms in the human body like carbon, hydrogen, oxygen, which are there in the body. To remove the inner shell electron in carbon, hydrogen, oxygen, a very low energy X-ray beam is actually best suited, and therefore when we use this low energy X-ray beam, more and more photoelectric effect occurs inside the human body. Now let us quickly revise Compton effect and photoelectric effect. We have just seen that. Let us quickly revise. What is Compton effect? It is an interaction of an X-ray photon with outer shell electron, whereas photoelectric effect is interaction with an inner shell electron. Compton effect is most common interaction. Photoelectric effect is relatively less common. Compton effect is called mid-energy phenomenon. Photoelectric effect is called low-energy phenomenon. We discussed this. What is the outcome? Result of Compton effect is scatter radiation, causes image blurring, image distortion. Result of photoelectric effect, there is no scatter radiation, so it improves the overall image quality. because it causes, Compton effect causes scatter radiation and image distortion, we want to minimize it. This can be achieved by using high energy X-rays. Whereas in photoelectric effect, there is no scatter radiation. So we actually want to maximize it. This can be done by using one, low energy X-ray beam, two, high atomic number target. And I hope you have realized by this time, in Compton effect, when the X-ray photon strikes the electron, only a small amount of its energy is lost, because that is a small amount of energy required to remove the outer shell electron. Whereas in photoelectric effect, when the X-ray photon strikes the inner shell electron, its entire full energy is being lost, isn't it? So this is an animated review of what is Compton effect and photoelectric effect. These two are the most predominant ones which are occurring clinically when we do X-rays, in clinical practice. Now let us look at the other three interactions. The first one we are going to study out of the remaining ones is called as coherent scattering. This is also called as classical scattering, or given certain names such as Thomson's scattering or Rayleigh's scattering. What is this? We'll discuss. See what happens. Look at the animation. An X-ray photon comes and hits an electron. It gives up all its energy to that electron. X-ray photon disappears. The electron gets excited, right? It has become excited. It has received a lot of energy. So what happens? This electron wants to get rid of that excess energy. So it vibrates, releasing an X-ray photon which was exactly identical to the original one, but in a different direction. X-ray photon strikes an electron, disappears, electron is excited, vibrates, release a similar X-ray photon but in a different direction. So what happens in coherent scattering? No ionization occurs. Only the direction of the X-ray beam changes. If this interaction involves only a single electron, coherent scattering involving only a single electron, it is called Thomson scattering. But if the coherent scattering involves all the electrons in the atom which are given energy, they get excited, they vibrate together and new X-ray photon is released, all electrons are involved, that is called as Rayleigh's scattering. Coherent scattering is not very commonly seen in routine clinical practice. The next one is what is called photo disintegration. Look at the name. Disintegration means something is going to disintegrate or break. What breaks is the nucleus of an atom. See, when a high energy X-ray beam comes and strikes the nucleus, because of this energy which is deposited, some part of the nucleus breaks off, disintegrates, and either an alpha particle or a neutron is emitted out. So the nucleus is fragmented, disintegrated. This occurs only if a very high energy X-ray beam is involved, a strength or intensity of more than 7 mega electron volts, and such a high energy X-ray beam is not used in clinical practice. So photo disintegration is not important clinically. So just remember the name, you'll automatically remember it when you look at the animation. Something is going to break, disintegrate. What breaks is the nucleus. We have seen that. Released is alpha particle and neutron may be released. Next is called as pair production. Again, look at the name, right? A pair is going to be produced. So what is going to happen? An X-ray photon is going to come and hit the nucleus, right? Nothing will happen to the nucleus, but the energy of X-ray photon is converted into particles or matter. One positron and one electron is released out. A pair is produced. Right, so energy is converted to matter, a pair of positron and electron is produced. This occurs again only if the incident X-ray beam is having a strength of more than around 1 mega electron volts, which is again not used in routine diagnostic radiology. So this is also an interaction which does not occur very commonly. Quickly, let us revise all the interactions that we have seen. Let us start with Compton effect. What is Compton effect? Look at the animation. It is an interaction of an X-ray photon with an outer shell electron. The result is that there is deviation of X-ray beam or scatter radiation which causes image distortion. So we try to minimize Compton effect. What is photoelectric effect? An X-ray photon comes and strikes an inner shell electron. Right, the X-ray photon disappears, there is no scatter radiation, it improves the image quality, and therefore we try to maximize the photoelectric effect. What is coherent scattering? An X-ray photon comes and deposits all its energy into an electron. The electron gets excited, it vibrates, releases an identical X-ray photon out but in a different direction. No ionization occurs, only the direction of the X-ray photon changes or X-ray beam changes. This is called coherent scattering. Photo disintegration, the nucleus is going to disintegrate. Very high energy X-ray beam comes and strikes the nucleus. A part of nucleus is broken off. An alpha particle or a neutron may be released. pair production is what. In pair production, what is going to happen is that an X-ray photon is going to come and strike the nucleus. Energy is going to be converted into matter. A pair of particles, a positron and an electron, is going to be produced. So this is the interesting, topic of interactions of X-rays with matter. I would have told it to you in a very factual manner, point by point, but then it would get very monotonous and boring. I hope you have loved this when you looked at it in an animated form here.